This is the recording for the Unit 6 homework quiz. So I'm actually looking at the unit folder here. So on the top you have the activities and assignments. There's a number of things to do. There is actually a couple more videos in here where it says watch the instructor's videos on heat experiments and the ideal gas law. There's the learning objectives. Then there's the homework quiz itself, of course, and as usual, there are the worked out problems, so please work through them and then look at, and of course they're here in the, also printed out in the worked out problems, so you have them on video as well as printed, and then see what the homework quiz says about that. Okay, this one is kind of out of the usual what I do. Here I had to put this one in to point out the difference between absolute temperature and a difference in temperature. So you look at this one here, and I will probably come across it in the homework quiz when I explain it. There's also something here out of the ordinary that's Start Your Engines. It's a really nice website that was actually taken off the web, but fortunately it's archived. And it really shows great animations of various heat engines. These are also out of the ordinary, so a number of heat experiments and gas law experiments that I do, which are covered on the homework quiz. By the way, this particular unit covers a total of 4 chapters, which is also a little bit more than usual. Okay, then of course you have to read through how everything works, and then you have a couple of videos from the mechanical universe. And it's an overview which you will find in this homework quiz. Okay, homework quiz. Question 1. Typical thing, just answer everything with yes here on the first question. On the second question, again, take an exercise from the book and answer it. Third question, these are the contents and objectives. I believe that all of them apply. Convert between various temperature scales, differentiate between heat and internal energy, and so on. I think you will see that all of these here will make sense. Okay, here's a content question. Temperature differences, delta T, may be expressed in Kelvin or in Celsius degrees. That's because they increase equally. For example, 15 to 36 degrees Celsius is a difference of 21 Celsius degrees, and the equivalent 288 kelvins to 309 kelvins is also 21 kelvins. So temperature differences can be expressed in either Celsius degrees. Notice that this is actually turned around. That means it's a difference or an increase in temperature, Celsius degrees rather than degrees Celsius, or you may express it in kelvins. Either way works for temperature differences only, not for absolute temperatures. Okay, so let's see. Temperature of an object was increased from 42 to 73 degrees Celsius. The temperature difference is 31 Celsius degrees or 31 kelvins. And again, it comes out to 31 either way. I believe all of these are in the correct order. Let's see, there are a couple more here. Absolute temperatures must be expressed in Kelvin. So before determining Carnot efficiency for a machine operating between 4 degrees and 25 degrees Celsius, these must be converted to kelvins, 277, 298 kelvins, and that particular computation then gives the correct result, in this case 7% for this particular efficiency of this particular machine. If you plugged in 4 degrees Celsius and 25 degrees Celsius for the absolute temperatures, that leads to a wrong result. So don't do that. There's a number of problems where you have to make sure that you have absolute temperatures in kelvins. And here I just put this one here in lighter color. If we use the American system, then the same would be for Fahrenheit and Rankine. For temperature differences, we could use either one of them, but for absolute temperatures, we would have to use the Rankine. All right, the last one here, the temperature of diesel air mixture changes adiabatically from 22 degrees Celsius to 533 degrees Celsius. If these temperatures are used as absolute temperatures, they must be converted to 295 kelvins and 806 kelvins, of course, by adding 273 kelvins, which is the temperature difference between kelvins and Celsius, to either one of those. And no, you may not use these for absolute temperatures. All right, these are from the worked out problems. They are pretty much in the correct order here, unless, of course, something reuses a different unit. The very first one here, I struck that out. I actually forgot why. Maybe it was an old problem. I don't know why I didn't take it off after all. Heat Q, quantity of heat, 1800, probably joules. However, down here is one that says heat Q equals 1400, and when you look at the original problem, you will find out that Paul Hewitt is actually using another older unit, which is the calorie. So this one actually goes with this one here. I really like to use the joule exclusively, but as I said in the book, occasionally he uses the calorie as well. Final temperature, TF equals 22.4 degrees Celsius. In this case, it is an absolute temperature, but you're not going to do a calculation with it. So what I said earlier, when you do a calculation with absolute temperatures, then they have to be in kelvins. But in this case here, this is actually the end result, 22.4 degrees Celsius or 295.4 kelvins. Expansion length, delta L, that's probably in meters. Again, look at these problems in the worked out problems and you will see how they match up. And I hope that you actually work through them. Then it goes all the way down to mass of the ice is 80, well, grams probably, that's why I put this one here. But then notice this one here, mixing temperature T equals 0, and if you go to the problem, it actually recycles the degrees Celsius up here. Turns out actually in the problems that Paul Hewitt has in his book, none of them actually comes up with an answer that is in kelvins. Somebody could say, well, the temperature difference back here, right here, that could be in kelvins. Turns out actually in the book it is in Celsius degrees. Okay, and then efficiency, that would be here in percent. I think I do have the percent sign. Yeah, it's right there. All right. So again, look at these problems. That's straightforward. And again, I hope that you work through these problems. This one here is about that really nice website with great animations that show the various machines. Unfortunately, it was taken off the web, but fortunately, it says archived. And just to be on the safe side, I actually did make a recording of it, so you can watch that as well. That recording is also posted in the Unit 6 lecture folder, as everything refers to the homework quizzes posted right there. Okay, I believe all of these are in the correct order. Let's just look at a few. So the 4 laws of thermodynamics. The first one is conservation of energy. The second one is about entropy. The third one is that absolute zero exists. And then physicists and chemists decided, oh, you know what, we should have defined temperature first. So instead of renaming them, we call it the 0th law of thermodynamics. Oh well. The Carnot cycle, when you see that on that Start Your Engines website, that's the description for it. You look at Heron's experiment, and you will see this is what it is. You look at Savory, Newcomb, and Watt Stirling engine. Let's see the Stirling engine. Let's see, I think it's this one here. As I said, these should be in the correct order. It's a device that converts heat into mechanical power by alternately compressing and expanding a fixed quantity of air or other gas, the working fluid at different temperatures. The Stirling engine, if you took the if you did the lab with me, then you came across it and you noticed, no, it's not working on water or steam. It's actually working on air. Explosion engine using gunpowder. Oh yeah, that's Huygens. So Huygens is, there he is. Yeah. And then the Otto engine, that is what we call in America the internal combustion engine, which is kind of interesting because the diesel engine actually is also an internal combustion engine. But this is what we usually call it. We call the diesel a diesel, but I guess we call the Otto engine the internal combustion engine. And you will see that these here are the statements that match with the diesel engine having a much higher compression ratio. And you will come across the Wankel engine, which in America is called the rotary engine. All right, next one here, heat experiments. These are also most likely in the correct order. Look at the videos that I posted here. In the meantime, if you look back into your own homework quiz, you will find I actually put in there that it says watch this video, which is posted here in Unit 6 folder. So bimetallic strip, you will find that one material expands more than the other due to its larger coefficient of thermal expansion. You will see the ring and ball experiment, and you will see that this is the explanation to it. You will see the copper rod with tightly rolled paper. Oh, I take that back. That's actually a little bit out of order. And you will see that the best correct explanation is metals are good heat conductors. So that's kind of like a little backwards here. Water boils beneath 100 degrees Celsius. Cooling there above the water increases the boiling point of water. So as I said, that's a little flipped here. Depression of thermometer reading when first immersed in hot water. So that's the explanation here. That's I really like that experiment. Well, I like them all, but that's kind of like one of my favorite ones. Rods with candle wax. And again, here is the explanation for that. Metal specimens on slab of wax. And here's the explanation. Then the thermos. Why does the thermos look the way it does? Then radiation cans, and again, that's a little backwards here. So dark colors radiate better than light colors. When you look at that experiment, there's the Franklin palm glass, which is this one here. So, oh, whoopsie, that goes with this answer here. And then I believe the last two are also backwards. There you go. So look at these explanations, look at the videos. Okay, then this is actually the same video, but there's a bunch of gas law experiments here, and that's why these matching statements look a little cryptic. So a fire syringe, when you look at that experiment, you will see that you have that piston that is just hammered into a tube, and there is a little piece of cotton in there, and it catches fire. And the reason is that as you hammer it down, you increase the pressure a lot, you decrease the volume obviously, but at the same time it's happening so fast that the heat that is being generated can't go anywhere, so it increases the temperature apparently above the ignition point of cotton, respectively, whatever other material I use in there. Bicycle pump, by the way, if you touch, as you pump up a bicycle tire, you will notice that the nozzle is really hot at the end, and the same thing actually happens. Increase the pressure, well, that's why you pump up. That's why you use a bicycle pump. You know, you increase the volume inside the pump itself, but the side effect is that the nozzle increases in temperature quite a bit. Then the ping pong ball, you will see that in the experiment that the temperature is increased, which increases the pressure inside the ping pong ball, and then that increases the volume and gets the ping pong ball to back to its original size. Weighted balloon in water, I believe, uses the same statement here. Again, look at these experiments, and then a lot of the rest here uses the other statements over here in the correct order. So C, D, E, F, G, H, I, up to slowly push piston into a barrel of a syringe. That's different from the fire syringe because this one is being slowly pushed. So when that happens, let's see, it says it uses statement G, you increase the pressure. At the same time, you decrease the volume, but because you do it slowly, as it's trying to heat up, that heat actually has the time to escape, and there's a negligible temperature increase. That's why it doesn't say anything about temperature here. And then the last ones here, each one of these is a two-part answer, so you would have to look at these statements here. And I believe they are in the correct order. All right, then you have to look through the assigned chapter in Bloomfield. So that's everything how how everything works, clothing and insulation in this case. I didn't check all of these. I have you read through it, but probably in there is conduction, emissivity, and thermal energy, and probably heat transfer, and maybe the Stefan-Boltzmann law. Again, look at it, and so on. Read through it. And then the mechanical universe, 2 videos. That's what you have to watch. So again, I'm going to give away that heat is the random motion. That's the first quote. And the Fahrenheit scale here is the 6th quote, so I give that away. And I think the others are kind of backwards. So if you look at these 4, I believe this is the 2nd, this is the 3rd, this is the 4th, this is the 5th. And the same thing for the other video. But don't take my word for it. I really want you to watch these videos as well. All right, that is, I think there is an extra credit question down here. Let's see. Yes, it is extra credit. So this was apparently, wow, that's been almost 10 years ago. Yeah, I had a little boy in the car who slept. I just drove by that business that had that temperature scale. I had that thermometer display on there that just was totally wacky. And over the course of 2 minutes, watch that little video. It's only 2 minutes long. It gave me all these temperatures. And you know, in August 2010, even in Soldotna, Alaska, oh, you know, it was -13 or -35 Fahrenheit, and it also was not 118 Fahrenheit. Which of the following measurements are outliers? Well, they're all outliers except this one. It really was a nice, comfortable 59 on that particular day. So you pretty much have to check all of them, but just for fun, watch that video as well. And that now is the recording for the Unit 6 homework quiz.